in terms of we talked about metals and nonmetals and the metalloids, right? We've done that? Yes. Hopefully shake your head. Yes. Okay, now we're going to break it down basically into the main groups, and we're going to talk about what those groups are called, and what they act like, right? What they look like, and what their chemical properties are. Okay? So when I say group 1, am I talking about a column or a row? A column, right? Groups go up and down. So group 1 is that group on the right of the periodic table or the left of the periodic table? Left, right? So group 1 is what we call the alkali metals. Okay, these are group 1. So the alkali metals, okay, are lithium, sodium, potassium, rubidium, cesium, and francium, are what we would consider the alkali metals. Even though hydrogen kind of sits on group 1, we don't consider it an alkali metal because it's not a metal. Okay, it's a non-metal. Hydrogen is a gas. Okay, it's a non-metal and it's a gas at room temperature. But it sits over there on the periodic table because it kind of behaves like that. It's only got 1 proton, 1 electron. That's why it kind of gets to sit over there on the periodic table. But these are the alkali metals. Really, from lithium down, anything in group 1 we consider an alkali metal. Okay? They have a silvery appearance. They're shiny. They're most of the time that silvery color. Okay? Again, hydrogen is excluded from this list, so don't think about hydrogen in that term. The alkali metals are really soft. So I've talked specifically about sodium being a really soft metal. That goes for all of those alkali metals. Right? Pretty soft. They do get a little tougher as you move down the periodic table, but still pretty much cuttable with a knife or a small like scalpel or something. Okay. These metals are not found in nature as free elements. Okay, so you're not going to be like just walking around and see a chunk of sodium metal. Okay, or lithium or any of those metals. You're not just going to see it sitting around. Does anyone have an idea as to why that is? The reason that they're not found in nature is because they're extremely reactive. We're right. Okay, very, very reactive. They want to bond with anything and everything to form a new compound. Does anyone know what happens when we put an alkali metal in water? Yeah, there's an explosion. Okay, and then we're going to watch a little quick video about that. Okay, so we'll see a couple examples of that. Group 1 has what we call a valence electron, and it only specifically has 1 valence electron. So every metal in group 1, every alkali metal has 1 valence electron. And what a valence electron is, you might want to write this one down. Valence electrons are electrons. Okay, that's how I write electrons. So anytime you see that E with a minus sign or a negative sign, I'm talking about an electron. Okay, so electrons in the outer shell. Have you guys heard the term valence electrons before? Okay, good. You're shaking your head yes. Okay, so they only have 1 valence electron, and a valence electron is an electron that's in the outer shell. Okay, so it's available to bond. If it's only got 1 valence electron, it wants to give it away so that it can have a complete happy shell underneath. Okay, it can have the octet underneath. We'll get to that eventually, but that's what a valence electron is. Okay, number of electrons in the outer shell is a valence electron, and group 1 only has 1. To the alkaline earth metals, these are group 2s. Okay, so what alkaline earth metal would be the starting of group 2? Tell me what element that is. Beryllium, good. Okay, so these are beryllium, magnesium, calcium, strontium, barium, and radium. Or radon? I can't remember. Radium, yeah. Radium's over there. Radon is over there. Okay, good. These take on a little bit different characteristics than the group 1s. Okay, they're a little bit stronger, they're a little bit denser, they're harder to cut. Okay. So we talked specifically last class about how groups give similar characteristics. So that's why we're looking at each of these groups specifically, because all of the groups share characteristics. So like, for example, group 1 we think of as highly reactive. and especially with water, they're highly reactive. Group 2s, now these all behave similar as well, but they behave differently from group 1. Okay, so we see how Moseley started putting together the periodic table, and we see this repetitiveness of characteristics. That's why it's organized by those groups. Okay, group 2s have higher melting points, so it's going to take more energy to break those bonds of that metal. Okay, higher melting points, which means it's a higher temperature that's going to start to melt that metal from a solid to a liquid. They are less reactive than alkali metals, but they're still too reactive to be found in nature. So same thing, you're not going to walk around and find a chunk of calcium sitting there, right? We usually deal in calcium in terms of other compounds. Can anyone give me a really common calcium compound? Yeah? Metals have 2 valence electrons. So group 1 had 1 valence electron. Group 2 had 2 valence electrons. Do we see a pattern kind of forming here a little bit? A little bit, okay? So we're going to break up the pattern here with the transition metals, but you can see that group 1 has 1 electron to give up. Group 2 has 2 electrons to give up, okay? So I want you to start noticing that pattern there. Here's a form of pure calcium. Like I said, you're not going to see this calcium metal like found in nature. You don't see little chunks of this metal floating in your milk, right? It's a different, it's a chemical, it's a calcium compound. Okay, so it's not just pure calcium metal that's floating around in your milk. Okay. All right, the transition metals or the transition elements, that's the group 3 through 12, so the big chunk in the middle of your periodic table are what we call the transition elements. Most of the time we even call them the transition metals because they're all metals in there, okay? So you'll most of the time hear them called the transition metals because they have very typical metallic properties. Okay, and here's a review of our metallic properties again. Okay, good conductors of heat and electricity. They have that shiny quality, which we might call luster. And metals are typically a little bit less reactive. These transition metals are less reactive than groups 1 and 2. Okay? Uh-huh.
So if you dropped like one of the...
Less reactive enough, okay, or non-reactive enough to exist in nature. Okay, so we might see pure zinc or pure iron, right? Those are things that we would notice or we would be able to find in pure form in nature. Okay?
The other metals?
The transition metals are very much kind of predictable. They don't follow those patterns as far as valence electrons go. When we get to group 13, then we can pick back up on that pattern. But the transition metals don't really follow that pattern at all. So that's a little bit tougher to identify the number of valence electrons for each of those. Okay, it's kind of a variety. They don't follow those patterns. When we get to our next group, group 13, it picks back up on that pattern of number of valence electrons. Does that make sense? Okay. So let's skip forward to group 16. Okay, the chalcogens. Okay, or also known as the oxygen family. Okay. So these are the group 16s now. We're going to skip over 13, 14, 15 for a second, talk about group 16s, which starts with oxygen. These guys are fairly reactive, but group 16 kind of has a wide range of properties, and I want you to look at your periodic table to try to determine why that might be. So if you look at group 16, take a look at it in terms of what happens as you go down in group 16. Why might it have a wide range of chemical properties? Yeah, atomic mass increases. Some of them are metalloids, some are nonmetals, some are full-on metals, right? And each of those three things take on different chemical properties. So I want you to understand that it's not just a group of all nonmetals. As you move down, we see some changes, okay? So group 16 has kind of a wide range of those chemical properties, okay? Oxygen is the only one of group 16 that's a gas at room temperature. All the others are solids. Okay, so there's a one change right there. If you look at our class periodic table, you'll notice that's the only red one in the group, right? So that's the only gas at room temperature. That's what those red molecules mean. Okay, gas at room temp. Only one. Group 16 tends to form compounds with metals. Okay, so group 16 likes to bond with things that are on the left side of the periodic table. Right, that's where we find all of our metals, is on the left side of the periodic table. So these group 16s, they like to bond with a metal. When we form that bond of something in group 16 with a metal, most of the time they are insoluble in water or not soluble at all in water. Okay, so here's a little bit more about group 16. We talked about the fact that they have wide chemical properties, a wide range of chemical properties, and it's because we determine they're nonmetals, metals, metalloids, or even these man-made metals. Okay, so if you take a look at the class periodic table, the ones that are kind of just the outlines, those are the man-made elements. Okay, the man-made or the synthetic elements. Here. Okay, I was going to ask you how many man-made elements. This is man-made elements. Okay, I don't know why it says atoms. I wasn't thinking apparently. Okay, there's only 35 man-made elements that have been made. Okay, there's been 35 elements that we've synthesized. We've been able to create these elements. Okay, in a lab setting, we've been able to create 35 elements. I need to fix that. I don't know why it says atoms. Okay, 35 elements have been man-made. That's a number that you might want to, like store away. You might be on Who Wants to Be a Millionaire someday. Okay, that question's probably going to be on there. Okay. Group 16 has 6 valence electrons. So here's where we pick our pattern back up. Okay, group 1 has 1 valence electron, group 2 has 2. Now group 16 has 6 valence electrons, so you just drop the 10, right? That's going to tell you how many valence electrons once you get on the other side of the transition metals. Okay? Very good. All right, let's look at the halogens. Anyone know what group the halogens are? 17. The halogens are my favorite group. Okay, I don't know why, but they are. They're my favorite. Okay, so these are group 17, which includes fluorine, chlorine, bromine, iodine, and astatine. This is the most reactive group of nonmetals that we have. Okay. Most reactive group of elements from group 1 or group 2. Okay, so these guys like to form what we call salts. Okay, so salt is not just table salt that we eat. There's lots of other forms of salts. Sodium chloride is an example of a salt, but there's lots of other compounds that we consider under the salt family. Okay, so I know that's a little bit tough to understand because we call table salt salt. But compounds that are formed between a group 1 or a group 2 element and a group 17 element are what we call salts. Okay. These group 17s can be both liquid, gas, or solid at room temperature. So if you take a look at our class periodic table, you'll notice that you've got reds, which are gases, bromine, which is a liquid at room temperature, and then iodine and astatine are both solids at room temperature. Okay, even though they're all in that non-metal family. These guys have 7 valence electrons. So group 17, 7 valence electrons, right? That pattern continues. Do we see what that pattern is happening? All right, good. Usually not found alone in nature. Can we guess why? Very reactive. Okay, they're very reactive. These guys are reactive, but they don't react with water. Okay, so it's not going to be reactive like the alkali metals reactive. But these guys want to bond with anything and everything. Okay, because they have 7 valence electrons, how many do they need to be complete and happy?
1.
They need 1. So they're going to take an electron from anything and everything they can. And think about this. Doesn't group 1 have 1 valence electron they want to give away?
Yeah.
Yeah. So they're going to pair pretty well together, right? Group 17 and group 1, they play really nice because one wants to give, one wants to take. So they bond a lot. Okay? Which, take a look, sodium chloride, how do I make that bond, right? How do I make that salt, or sodium chloride? Isn't sodium in group 1 and chloride in group 17? All right, that follows what we want. Sodium and chloride are going to give up those electrons to make each other happy. Okay, the noble gases, anyone know what group? 18, good. The noble gases are group 18, so helium, neon, argon, krypton, xenon, and radon. All in group 18. Reactive. These guys are blah. Okay, they don't do anything. They don't want to bond with anyone. They don't want to do anything. Okay, they're unreactive. And they are all gases at room temperature. Okay, all gases at room temperature. Which is why they're called the noble gases. Okay, they have a full outer shell, which includes how many electrons? 8. Good, I'm glad you guys already know that. Okay, they have a full octet. That's what we call it, a full octet. All 4 of those noble gases are used in neon lights, even though they just are called neon lights. They use more than neon. Yep. Top of the bottom, right? Okay. So, as you look at this pulled out section right here, this top row, starting with lanthanum. Yeah, I don't even know how to say that. We never deal with that. Lanthanum, I guess. I don't know. It tells us that's the lanthanide series. Okay, because it starts with La. So this is called the lanthanides, or the lanthanide series. These are atomic numbers 58 or 57 here. 58. Sometimes you'll see 57 included in there through 71. Okay, and sometimes lanthanide and lanthanum and actinium, or however you say the next one. Yeah, actinium. Sometimes they're left up with the regular periodic table. Sometimes they're pulled down. I don't know why. Okay. In our case there and on here, they're both pulled down. So it's really 57 through 71. You just need to understand which row is which one. Lanthanides are the top row, actinides are the bottom. So these are shiny metals. They react similarly to the group 2s, which are called, what's a group 2 called? Alkaline earth. Okay, good. So the actinides are the row that sits right underneath, or the period that sits right underneath and starts with actinium. Groups 89 or 90 through 103, or atomic numbers 89/90 through 103. Okay, so the lanthanides and actinides are both pulled down underneath that periodic table. These are the radioactive elements. The actinides can carry mostly man-made elements. Okay, mostly those radioactive elements are man-made or synthetic, but some of them are actually found in nature. Both the lanthanides and the actinides, or the lanthanide series and actinide series, sometimes you'll hear them called that, they're placed below the periodic table to save space. Okay, I'll show you what it would look like if we left them in there, and it throws the periodic table off. It would make it pretty hard to look at. Okay. So let's see what it would look like if we kept it included in there. Okay, the lanthanides and the actinides make it a little bit difficult to read, right? It'd be hard to fit that on a sheet of paper that makes sense. So the lanthanides and the actinides are really just pulled down to save space. The reason it's not just rearranged to fit everything in complete a square, right, or a rectangle, is because we still want it organized by chemical properties. Okay, so the reason we don't just list them in a rectangle 1 through 118 is because we still want it to be applicable to those chemical properties. We still want the patterns to show up. So we just remove that group, keep the transition metals in there to keep it in a little bit of better shape. Okay, does everyone get what they need to off this slide, or are we good there? Okay. We didn't talk much about group 13, 14, or 15. The only thing that I really want you to understand about 13, 14, and 15 is that group 13 would have 3 valence electrons. Group 14 would have 4 valence electrons. Group 15 would have 5 valence electrons. That's really the only pattern I need you to look at there. Otherwise, they have pretty varied chemical properties, just like group 16 did. Okay, so we're not going to go over those in depth. They don't really carry anything super special, but I just need you to understand that valence electron pattern. Cool? All right, very good.